Hello everyone, and thank you for joining us for today's Surface Measurement Systems live webinar. The title of today's session is The Impact of Relative Humidity on the Adsorption of Volatile Organic Chemical Pollutants by Porous Materials. And we're very lucky today to have with us our Associate Director of Scientific Applications, Dr. Majid Naderi. Now, before we progress with today's presentation, I just wanted to remind the audience of some of the housekeeping rules for today's session. We do ask that everyone keep their microphones muted throughout the duration of the presentation, just so Dr. Naderi's audio quality isn't interfered with by any background noise or feedback loops, and just to make sure everyone's able to enjoy the presentation at the utmost quality. Excuse me. And I would also like to remind everyone that you have the opportunity to engage Dr. Naderi at the end of today's session in a live Q&A session. So there are two ways you can submit questions for this. If you would like to unmute your microphone and ask the question directly over your mic, you can do so simply by raising your hand at the Q&A session, and I will let you know when you can unmute your microphone and you can ask the question directly. Or if you prefer to submit your question in writing, I will pose the question to Dr. Naderi myself. So just submit that in the questions tab in the webinar control panel. So as mentioned, today we're lucky enough to have Dr. Majid Naderi with us to explore this topic. Majid received his master's degree in petrochemicals and his doctorate in the synthesis of novel catalysts, which was sponsored by Shell, from the University of Manchester Institute of Science and Technology in Manchester, UK. He joined Surface Measurement Systems in 2002, using his background in physical chemistry and its application to the characterization and development of inorganic solids. Dr. Naderi is the Associate Director of Science Applications for SMS, with a responsibility for the application of dynamic vapor absorption and inverse gas chromatography for materials characterization, using a broad range of materials, including pharmaceuticals, catalysts, and polymers. Dr. Naderi has delivered a number of international lectures and is author and co-author of more than 40 scientific papers and posters, as well as a chapter book on the methods for measuring BET surface area. So once again, remember, you will have the opportunity to pose your questions directly to Majid at the end of today's session. So make sure you stick around for that at the end. So without further ado, I would like to hand over to Majid to begin his presentation.
Thank you very much, John, for the introduction. And so I'm sharing my screen. John, can you see my screen as well?
Yes, all clear.
Great. Good day, everyone, and welcome to today's talk on the impact of relative humidity on the adsorption of volatile organic chemical pollutants by porous materials. I'm going to I'm going to start with a little bit of introduction to the adsorption science and DVS technique before moving to some applications and case studies, including the impact of humidity on surface area and why there is so much interest in gas absorption and vapor absorption. Excuse me, let me just get my pointer. Right. And also, I'll be showing you our DVS data on solid state adsorbents for vapor and gas absorption to demonstrate the performance of adsorbents with or without background humidity. For the absorption processes, the majority of studies concern the absorption of pure gases or vapors, but in the real world conditions, you would expect other molecules to be present too. The concentration of water molecules, for example, would be more than other vapor and gas molecules, and it is important to measure the performance of adsorbents in the presence of humidity. So we are going to demonstrate application of dynamic vapor absorption as a characterization technique that would consider several experimental and environmental conditions at the same time for the removal of VOCs and CO2 gas. Using molecules as a probe, we can study the interactions with the materials under investigation. Molecules are either adsorbed on the surface or absorbed into the bulk of the material. Adsorption can be classified as physisorption, where molecules will attach to the surface in the form of an adsorbed layer. Absorption can be classified as bulk absorption or absorption into the lattice structure, where molecules will diffuse into the bulk of the solid. So there may be monolayer formation, multilayer formation, or condensation. Monolayer formation in the form of a uniform layer of molecules attaching to the surface of the material, and then as the concentration increases, more layers are built up on top of the first layer, and you have multilayer formation. And for the case of condensation, it could be a cluster formation of isolated clusters of molecules on the surface of the material, or capillary condensation into the pores, for example. Here is a schematic diagram of a typical DVS system. There are two sets of mass flow controllers where they control the flow of vapors. Two sensors. One is the protronic probe for the humidity generation, and the other one is the speed of sound sensor, which is a unique sensitive sensor for organic vapor, and it is unique to our DVS system as well. And then once the vapor is introduced into the system, the sample, which can be preheated or preconditioned at higher temperatures using a preheater, is then exposed to vapor, and any mass gain or mass loss is then registered by a microbalance. There is also an exhaust flow, which can be directed to a fume hood or can be attached to another system like a mass spec for further analysis of the gases released. Typically, the kinetic data are basically registered against time. So you have here, for example, the generation of water or any other vapor, and then the red line, the solid red line, shows the changes in mass. So after each stage, once the equilibrium is established and the mass is stable, the system automatically moves to the next stage. During the absorption experiment, the generation increases, and during the desorption, the generation obviously decreases. Now, if we take the changes in mass and plot them against relative humidity or concentration, you'll see that you can plot the isotherms. The solid blue line is the absorption isotherm, and the dotted line is the desorption isotherm. The differences between the absorption and desorption branches of the isotherm form the hysteresis gap, and the gap between the two can give you additional information. And generally, the form of the shape of the isotherm and the hysteresis gap can tell you additional information in terms of the sample's behavior and also the absorption mechanism, and whether you have monolayer, multilayer formation, or condensation in the sample. One of the properties that can be measured with DVS technique is the BET surface area, as it is important to have an appreciation of how surface area of materials changes due to different processes. For example, how surface area changes as basically increases as the particle size decreases here. So comparing different methods, DVS, IGC, SEA, and nitrogen absorption technique, both DVS and nitrogen absorption technique can measure high surface areas. But for DVS, you can measure surface area at ambient conditions, whereas with nitrogen technique, you would need liquid nitrogen and vacuum conditions. So for some materials, it is important the stability of the material suffers under these conditions, and DVS would be more ideal. Also, another point to note is that for the nitrogen absorption technique, any measurement below 1 square meter per gram wouldn't be as accurate as DVS, where you can measure surface area values below 1 square meter per gram as well. Here is an example of surface area of an alumina sample at different humidities. So at 0% relative humidity, the BAT value of 2.95 square meter per gram is in good agreement with nitrogen absorption measurements as well. And as we increase the relative humidity to 50%, the surface area drops. And when we go to 90% relative humidity, the surface area drops significantly. And this is due to water molecules competing for sites or blocking the available surface area on the material. For porous materials like zeolites, gas absorption would be more significant, whereas for non-porous materials like food and pharmaceutical materials, vapor absorption would be more significant. So for our experiments, we would be looking at the amount of mass change when a sample is exposed to different environmental conditions, controlled humidity and controlled ethanol, methanol, and CO2 concentration. It would also be possible to quantify the amount of adsorbed gas and vapor by using a new member of the DVS family, the DVS breakthrough analyzer. Unfortunately, time wouldn't allow me to go through the available data on this system, but this is something that we will cover in future webinars, and it's something to look forward to. Applications of adsorption processes. Adsorption is generally a common process used in industry for various non-catalysis applications, such as purification for removing impurities from a gas or liquid stream, depollution, decolor, deodor, and solvent recovery. The process usually requires regeneration of the saturated adsorbents, and common adsorbents are molecular sieves, activated carbon, silica gel, activated alumina, and metal organic frameworks, MOF materials. So this slide shows a study on the removal of volatile organic chemical pollutants from the air we breathe indoor and outdoor. VOCs can be released from a wide range of sources, including inside the houses and industrial places. Recently, concerns have moved from environmental to a health problem, as increased levels of VOCs have been linked with respiratory diseases. So VOC molecules include toluene, formaldehyde, xylene, acetone, and benzene, which may appear in different forms, as in solvents or paints and packaging materials, and basically all the materials, building materials, and whatever we are dealing with in everyday life. It is therefore important to find a solution for the removal of these pollutants from the air, and studies have focused on the synthesis and design of porous adsorbents with high surface area, including MOF materials and porous polymers, but zeolites and activated carbon materials are widely used due to their low cost of production and their availability. VOC concentrations can vary in different environments, but are significantly lower than the moisture concentration. So water molecules would be competing for the same adsorbent sites as VOCs, and it would be important to assess the impact of humidity on the choice of porous material for removing VOC molecules. Here we look at the impact of humidity on a series of common industrial porous materials like activated carbon, amorphous silica, zeolite 13X, zeolite Y, and ZSM5, which are potentially used for capturing VOCs. I'm going to show you single component experiments using water or organic vapor molecules, as well as a combination of both components, water and organic vapor. Here, the water absorption isotherms show that zeolite 13X has the greatest affinity for water, but for toluene and ethanol, the isotherms show a different behavior where activated carbon sample here picks up a substantial amount of toluene and ethanol, whereas zeolite 13X has a much smaller uptake. So moving from a polar probe molecule like water to a non-polar molecule or less polar molecule, there is a significant difference in single component uptakes where activated carbon appears to be best for the removal of the organic vapor. However, in the real world conditions, both water and toluene molecules are competing for the porous materials, and we need to investigate the effect of humidity by running a dual component experiment. Okay, now let's look at the, the two component DVS data where we have studied the impact of humidity on adsorption of toluene and ethanol by measuring toluene adsorption at 0, 10, 30, 50, and 70% relative humidity to represent high and low humidity conditions. Now, under dry conditions, 0% relative humidity, activated carbon takes up a significant amount of toluene, over 25%, and even at 10 and 30% RH, the performance of activated carbon is greater than the other adsorbents. But moving to 70% RH, the toluene uptake drops by a factor of 10, whereas activated carbon would be ideal for removing VOCs in dry conditions, it wouldn't be ideal adsorbents for removing VOCs in humid conditions. Now, the interesting performance comes from zeolite Y, where the uptake was relatively lower than activated carbon. That's about 12.5%, but its performance was independent of relative humidity. So it appears that the hydrophobic sites in zeolite Y are ideal for VOCs, and they are not compromised by water vapor molecule. To see the reproducibility of these experiments, we performed a series of experiments, different cycles, 4 cycles, and during the multi-cycle adsorption experiments for toluene at 0% and 50% RH, we can see reproducible for behavior for most adsorbents except activated carbon, which loses performance during the regeneration at 0% and 50% RH. Zeolite Y shows a relative performance of more than 98%, similar to activated carbon. Here, the amorphous silica and zeolite 13X show a very negligible amount of toluene at 50% RH. So, in summary, single component adsorption studies provide some information on choice of the best adsorbents, but 2 component experiments provide more conclusive data for VOC adsorption in the presence of a range of relative humidities. Here is another example on methanol and water adsorption on a polymer film, where basically methanol on its own and water on its own, and methanol and water together have been generated, and the sample has been exposed to these vapors at 2 different temperatures, 25 degrees C and 45 degrees C. So we can see the red line shows the mass change at 25 at 45 degrees C, and the blue line shows the mass change at 25 degrees C. For methanol on its own at 50% concentrations, as we increase the temperature, there is no change in uptake really, so it's more or less the same uptake. Moving to water at 20% relative humidity on its own, no methanol, the uptake increases slightly as we increase the temperature. But the more interesting part is the methanol and water absorption, and you can see that the uptake increases as we increase the temperature. This is due to structural changes in the material, which allows more vapor to be absorbed. In another case is the absorption of ethanol and water in zeolite 3A. Zeolite 3A, the pore dimensions are big enough for water molecules to enter the pores, but are not big enough for ethanol molecules. So if we study the ethanol absorption on its own, pure ethanol, we don't see much uptake. It's below 1%, which is typical surface absorption. Whereas with water and ethanol mixture, you would see an uptake over 10%, which is mainly due to water uptake. So this would be potentially an ideal situation for separating water from ethanol. Another study shows the methanol absorption isotherm on zeolite 4A in the presence of 10% humidity. So we have 10% water concentrations, and then after 400 minutes, we introduce methanol into the system, 5% and 10% steps. So initially, we see a huge uptake due to a water uptake, and once we've got equilibrium, here we introduce methanol, and you see another increase in uptake. And as we increase the concentration of methanol, you see another small uptake before the mass drops. This change in mass basically indicates methanol replacing a heavier molecule in the material. For gas absorption measurements by DVS, here we have an example of a synthesized MOF material and modified, fluorinated, and for the water absorption single component experiment, you see a huge uptake at around 40 up to 40% concentrations, which is due to pore filling. And then a smaller uptakes and up to 90% concentrations, and then we come to desorption, half cycle, and basically all the water comes off. If we plot the mass change data against concentration, we'll see the isotherms here, which basically the blue line shows the absorption isotherm, and the red line the desorption branch of the isotherm, and the gap is due to hysteresis or the capillary condensation. Here on the right, you'll see the CO2 absorption isotherms on the synthesized material, and then modify them, unmodified and modified MOF samples. And you'll notice that the uptake is very similar for both materials, up to 60% concentration of CO2. And after 60%, the uptake for the modified sample drops, probably due to reduced pore volume for the fluorinated material. Moving to the competitive absorption experiments, here we equilibrate the sample by introducing 5% humidity, and then the red curve shows the increase in mass due to water uptake, and as it becomes to equilibrium, we introduce CO2, where you see another increase in mass. And when we stop introducing CO2, the mass comes back to where it was before. So clearly, the mass increase here is due to CO2. So what we can tell from the results is that water and CO2 are not competing here. Once water is adsorbed, CO2 won't be replacing it. So for now, we can agree on that for this particular material. But how about other materials? How about commercially available materials? How would they behave under similar conditions? So here we have the same materials, the modified and unmodified material or MUF samples exposed to relative humidities from 0 to 20% RH. You can see there isn't much difference between the two samples. There's slightly higher uptake for the modified sample at lower levels of humidity, but generally speaking, both behave similarly. If we move to the commercially available samples, MUF samples, we will see that this is very interesting, and we will see that the amount of CO2 taken up is affected by the percentage RH. So for HCAST 1, for example, the uptake is quite high, but at 20% RH, the CO2 uptake drops by a factor of almost 3. So although these samples, they show lower uptake, but are not significantly affected by the humidity, and they are more stable in the presence of humidity. So this is the basically more desirable property which can be investigated. So DVS is a versatile tool for studying vapor and gas absorption behavior of a wide range of materials, and is a fast technique for rapid screening of solid sorbents for CO2 capture. Gas diffusion as a function of relative humidity can be determined by DVS, and also DVS can offer measurements on vapor pressure and heat of evaporation of solids, gas absorption, co-adsorption, and vacuum drying. The new DVS breakthrough analyzer can measure quantitatively competitive adsorption and co-adsorption, but we've left this for future webinars and something to look forward to. And finally, I'd like to thank all my colleagues at Surface Measurement Systems, and special thanks to Elwin and Paola from Imperial College, under the supervision of Professor Darrell Williams, for the data on the adsorbents. And thank you very much for your time and attention. I'd be happy to answer any questions that you may have.
Thank you, Majid. And yes, we'll now be having our live Q&A. So just a quick reminder to our audience, you can either raise your hand and I'll let you know when you can unmute your microphone to ask your question of Majid, or you can submit your question in the questions tab. So just an initial question here to get us going, Majid. Someone has asked, did you use the step method or ramping method for these experiments?
All right. Okay. For these for these experiments, you can use the ramping method, but for our purposes, we just wanted to see equilibrium at each step, at each stage, and we used the step method. But for the ramping methods, the important thing is to have a low, very small ramping rate, and by all means, you can use the ramping method for screening of the samples as well.
Thank you. Claudia Arnold has asked, how would one handle adsorption questions with adsorbatives which diffuse extremely slowly, such as higher nitrogen alkynes on zeolites? Is it possible to do a DVS with such adsorbatives?
Is it possible to, sorry, could you read that again?
Yeah, so how would one handle adsorption questions with adsorbatives which diffuse extremely slowly, such as N-alkanes or zeolites? Is it possible to do DVS with such adsorbatives?
Yes, of course. I mean, the experiments, the advantage of DVS instrument is that you can design different experiments according to the nature of the material. And for the slow adsorbents, there are different ways of speeding up the experiments, and one is by using different carrier gases like helium, so or different temperatures. So you can increase the diffusion into the material by applying different methods. And the other thing is that again, for slow adsorbents, you could use, or you can optimize the mass of the sample and preconditioning, which would help.
Brilliant, thank you. Miles Boss asks, how is water diffusion in a porous material determined by DVS?
For diffusion, we do different diffusion experiments for films and powder samples. We have application notes which I can send you. Basically, for film materials, we have a special cell which can basically seal the film into 2 layers and measure. There is a cup which can be filled with water or moisture gather materials, depending which way you want to do, and basically measure the escape of water from the cup through the film, or absorption of vapor through the film by the moisture gather materials. That's for the films. For the powders, for the films, you can also hang the films from the hang-down wire and measure the diffusion on both sides of the film. But for the powders, you can basically put the powder into the sample pan and run the experiment, ideally collecting fast data. Basically, every 1 second, you need accurate measurements of the uptake, and the particular sort of relative humidities or concentrations you are interested in. You can collect data, and the software would allow you to calculate the diffusion coefficient as well as permeability into the sample.
Brilliant, thank you. Vahid Rahmanian has asked, did you try other types of MOFs like ZIF or UIO66 families for carbon dioxide adsorption?
Yeah, I must admit, I haven't done this in running more samples, and we will update through webinars any more materials that we test. But for now, we haven't tried those yet.
Thank you. Carlos Ibanez asks, did you change the regeneration conditions of the materials when exposed to water vapors compared to 0% relative humidity tests?
Yes, of course. These were done, but at 0% and 50% relative humidity. So these are the 2 conditions that we used for the regeneration. And yeah, as yes, here you can see the data, and for the toluene adsorption, you can see the activated carbon, basically the drop in performance after 50% 50% relative humidity and 0% relative humidity. They behave similarly. So there is a drop in performance under both conditions.
Great, thank you. A question here from Meishan Go, and she asks, for the carbon dioxide adsorption experiment, is it performed under vacuum condition? Can we do it at an atmospheric pressure?
Well, very good question. Thank you. That's these for the CO2 gas absorption experiments. They were all done under vacuum conditions. We are working on our system to perform the same experiments with the flow system, which is basically DVS resolution or Endeavor. and our engineers are working on it. We are not quite there yet, but it should be possible. If you are if we are basically working on CO2 adsorption on its own, that should be possible. But if you want to do competitive adsorption, CO2 in the presence of humidity, for example, then that's a little bit tricky, and we are working on it. So in terms of mass flow controllers and the sensors, we have to work on it to be able to detect both vapors and gases. And like I say, we're almost there.
Brilliant. Someone else has asked, have you tried these experiments at temperatures above 25 Celsius?
Again, another good question. Thank you. The short answer is no, but we decided to go for 25 degrees C because it's closer to real world conditions. But of course, it is important to try and do higher temperatures as well. And I think my colleagues are working on that as well.
Mariam Zuari asks, can you give some information about the shape of the adsorption desorption isotherms? What does it mean to get separated and irregular curves?
Right, thank you for that question. Yes, we have application notes. Again, I can send you the application notes, which would cover this in more details. But there are different shapes of isotherms. I mean, for example, shape type 1 isotherm would show for microporous materials very quickly. There is an uptake at very low concentrations. You see an uptake.
Can I give you the screen, Richard? Have you got an example in front of you?
Yes, I can. Maybe I can load that. Sorry. Let me just. Okay, so. Sorry, it's taking some time to load. Yeah, but yeah, generally the shape of the isotherm would tell you additional information about the absorption mechanism, and I'm just trying to load a few examples to see whether relevant to. Okay, here we go now. So, John, can you see my screen now?
Yes, now.
Isotherms. Okay, so as you can see here, the different shapes of isotherms could indicate the materials basically characteristics and the shapes of the pores. In this case, the hysteresis gap, for example, here, it shows that we have interconnecting non-uniform pores. Now, if we move to this shape of hysteresis gap, for example, its characteristics of porous materials, like layered materials, very much more like carbon materials. And yeah, this is another example, which you can see. This is due to capillary condensation. This is typical of mesoporous materials where you have cylindrical pores, and just the way the pore is filled with molecules. Basically, it starts from the wall. Molecules build up, first layer, second layer, multi-layer, and then at some point in the middle, the two layers meet up, and then there is condensation in the pores. So that when it comes to desorption, the way the molecules go into the pore and the way they come out of the pore the speed is different, and that gives rise to this basically hysteresis here, which is typical of mesoporous materials. But like I said, I would be quite happy if John will have your details. I'd be quite happy to send you the full application note, which describes all of these isotherm shapes and hysteresis gaps.
Brilliant, thank you. A question here from Yoshiyuki Yamada, and they ask, what kind of amorphous silica did you use? I think you used ID type according to the isotherm. Why didn't you use B or A type or amorphous silica?
Well, this amorphous silica was, I think, was commercially available. We wanted to have an off-the-shelf material, and this was high-silica amorphous material we wanted to use. But of course, we, you could use different types of amorphous silica as well. But for our studies, that was, I think, was commercially available, and we wanted to use a commercially available off-the-shelf material.
Thank you. Chunyan Hao asks, can the surface measurement used for cotton? Can the surface measurement be used for cotton fiber materials, say coated with polypyrrole polymers?
Oh yes, of course. Thank you for that question as well. That's we can use any materials really, fibers, powders, films, and yeah, as long as the material fits into the sample chamber, we could use any kind of materials, and even with the bigger size samples, we have expandable manifolds that can accommodate bigger samples as well. So the samples can go into the sample pan, or they can be hung from the hang-down wire, and yeah, any type of material would do.
Brilliant. And a last question here from Ojualape Oganatega, and they ask, how are multi-component loadings measured?
Multi-component
Hello, Majid?
loadings. Is it for multi-component vapors? Then, do you have any clarification on that, John?
Yes, he said for multi-component vapors. Yeah.
Well, basically for multi-component materials. Okay. So basically for multi-component materials, again, it's the same as normal experiments, but the only difference is that unless you have a reference material, pure material, we wouldn't be able to tell which component is basically picking up how much of the vapor. So it would, a few experiments would be required. Ideally, one of a pure component, and then the mixture. And then you can basically subtract the baseline or the bench line from the mixed results.
Brilliant, thank you. I think that's all the questions we have. So thank you again so much, Majid, for being with us today to give your presentation and to take the questions from our audience.
Right, thank you very much.
And thank you again to all of our attendees for joining us today. On screen now is just a quick reminder of a few of the upcoming webinars and educational events we have coming up in the next month or so. Keep an eye out, as we will be announcing more dates for later November and December on our website in the next week or so. So make sure you check back at surfacemeasurementsystems.com/webinars to find out about any of those. And just a quick note to the few people who have been asking for some of the application notes mentioned. We will be making we'll make those available to you. We'll send them to you after the fact via email. And yes, the presentation today will be recorded, so that'll be available on our YouTube channel in the next week or so. So make sure you check back to find that. Otherwise, thank you again to everyone for attending, and thank you again to Dr. Naderi for being here with us today. Wherever you are, thank you once again from Surface Measurement Systems, and have a wonderful morning, evening, or afternoon. Thank you.
Thank you all. Bye-bye.